the Lowry Bronsted theory of acids and bases. I have to tell you, because I just googled it on Wikipedia, Brønsted-Lowry or Lowry Bronsted are two different people. Johannes Nicholas Brønsted and Thomas Martin Lowry both came up with the same concept in 1923. So they both get credited with this concept that we're about to talk about. So, an acid is a substance that donates a proton. And by proton, remember we're talking about a hydrogen ion. A base is a substance that accepts a proton. It's a hydrogen ion, the proton. So acids donate, bases accept. One way I think of this is talking about money and banks. ATMs, A for acid, give you money. Bases or banks will accept your money. Going back to the hydrogen ion for a minute, a hydrogen atom consists of one proton and one electron. Thus, a hydrogen ion that has lost its electron can be considered a proton. Remember, generally there are no neutrons involved in a hydrogen. So this is what we're talking about. We've got an acid, and it is a proton donor. We've got a base, and it's a proton acceptor. So an acid will give its proton to a base. The acid donates, the base accepts. So here's an example. Hydrochloric acid will give its hydrogen ion to water, H2O, to make hydronium, H3O positive. Water in this case is acting as a base, and we'll discuss water down the track. It's called an amphiprotic substance. Conjugate acid-base pairs. An acid gives up a proton to form a conjugate base. A base will accept a proton to become a conjugate acid. So an acid, when it loses its proton, it will become a conjugate base, and a base, when it accepts a proton, becomes the conjugate acid of that base. This diagram shows it very well. So an acid, if this acid donates its proton to this base, the acid has lost its hydrogen, so it now becomes the conjugate base of that acid. If that same conjugate base was to accept a hydrogen ion again, it would become the acid that it originally was. So the difference between the acid and the conjugate base of that acid is that it has lost one hydrogen ion. So the base has gained from this reaction. It gains a hydrogen ion to become the conjugate acid of the base. So basically it has gained one hydrogen and it becomes the conjugate acid of the base. Again, this conjugate acid, just by losing one hydrogen, becomes the base again. Here's another way that it's set out. So you've got the acid. Remember, an acid always has to have a hydrogen in it because it needs to have a hydrogen to donate. So we've got the hydrogen donor acid here. It will react with a base, which is a hydrogen acceptor. Something needs to donate the hydrogen, which is the acid, and the base needs to accept it. So when these two react, what happens is you are left with A minus, which is the acid minus the hydrogen, and this is called the conjugate base. The conjugate acid here is the base that has gained one hydrogen ion. So this is called the conjugate acid of this base. So here's a proper example. You've got nitric acid plus water. Nitric acid is an acid. When it loses that proton or that hydrogen, it becomes NO2 negative, which it is here. So NO2 negative is one hydrogen less than the acid was. So this is the conjugate base of nitric acid. Water here is acting as the base by accepting one hydrogen atom or ion. So water becomes hydronium H3O positive, which is then the conjugate acid of this base. The difference between the acid and its conjugate base is that it's lost one hydrogen, and the difference between the base and the acid is that it's gained one hydrogen. And that's the only difference between conjugate acid-base pairs. Here's another example. Hydrogen sulfide is acting as the base, and hydrogen fluoride is the acid. Hydrogen fluoride will give up or donate this hydrogen to hydrogen sulfide here. So the conjugate base of this acid will just be the fluoride ion, which is just the negative. It has lost this hydrogen. The conjugate acid is H2S. It has an extra hydrogen to its original base. So again, the difference between the base and the conjugate acid is the addition of one hydrogen, and the difference between the acid and the conjugate base is the loss of one hydrogen ion. So in summary, conjugate acid-base pairs differ by one proton. To find the conjugate base of an acid, you simply subtract one hydrogen ion. To find the conjugate acid of a base, you add one hydrogen ion. So from a conjugate acid to the conjugate base, you take off a hydrogen ion, and from the conjugate base to the conjugate acid, you add a hydrogen ion. It's that simple. And here is another example here. And another example you can have a look at. So hydrochloric acid and a base becomes the chloride ion here, which is the conjugate base of HCl because it has lost the hydrogen ion. Hydronium is the conjugate acid of H2O because it has gained a hydrogen ion. When acid-base in reactions involve the transfer of a proton from an acid to a base, it's known as a neutralization reaction. So it's basically an acid-base reaction. Okay, here's 3 questions for you to do based on that. So pause this, have a go at writing the conjugate acid and the conjugate acid and the conjugate base of these substances. Remember, it's the difference of one proton. Okay, so the answers to these guys are ammonium, extra hydrogen, hydrogen carbonate, extra hydrogen. Remember, conjugate acid, you add a hydrogen, and the formula for the conjugate base, you do the opposite. You take off a hydrogen, so you end up with HSO4 negative. Okay. Something else we need to talk about, a couple of other terms. Monoprotic acids. The word mono means one. Monoprotic acids donate one proton. So something like hydrochloric acid, it only has one proton, so it can only donate one proton. Nitric acid only has one proton, only can donate one proton. We also have polyprotic acids, and these are acids that can donate more than one proton. Remember the word poly meaning many, as in polymer. You have diprotic acids, di meaning two, and they can donate 2 protons. Things like sulfuric acid, carbonic acid have 2 protons. You also have triprotic acids. These can donate 3 protons, tri meaning 3. Phosphoric acid and boric acid are 2 examples. They have 3 hydrogens, so they have the capability of donating more than 1 proton. Doesn't mean they always do, but they have the capability of doing so. So these polyprotic acids donate their protons in stages. So you'll see here with sulfuric acid, it reacts with the water, it gives up one hydrogen to become HSO4 negative. That's stage 1. This HSO4 negative now can lose its hydrogen. So this is the same substance that was formed here, reacts with water again to form hydronium plus SO4 2 negative, and that's the second stage. So the product of the first stage can react again with the water to undergo the second stage. Here's a good example here with phosphoric acid. So phosphoric acid is a triprotic because it's got 3 hydrogens. At this point here, phosphoric acid can only act as an acid. It can lose 1 hydrogen to become H2PO4 negative. Why does it get a negative charge? Because it's lost 1 proton. It's gone from having 3 protons to having 2 protons. If it loses another hydrogen, it becomes HPO4 2 negative. Again, increasing that negative charge because it's lost a proton. And for the third proton it loses, it becomes PO4 3 negative. This substance here can only act as a base. It can only accept protons. Phosphoric acid can only act as an acid. It can only get rid of protons. But here you have these 2 very interesting substances that can act as either acids by losing, or by gaining a hydrogen, it can act as a base. So if one of these goes in this direction, it's gaining a hydrogen, it acts as a base. However, if it loses a hydrogen, it will act as an acid. These are called amphiprotic substances. Amphiprotic, you may have, I think of ambidextrous. Ambidextrous, you're left-handed and you're right-handed. Amphiprotic means that they're either acids or bases, or they can act as either acids or bases. So they can either donate or accept that hydrogen, as we just saw. The way they react depends on the relative strength of the acids and bases they are reacted with. So if you have a look in this example here, I've got HCO3 negative, hydrogen carbonate. Hydrogen carbonate with water. Hydrogen carbonate will act as an acid. Oops, sorry, I lost my cursor. It will act as an acid. It will donate its hydrogen to the water to form hydronium and carbonate. If you put the hydrogen carbonate here, the hydrogen carbonate ion, with ammonium ion, this ammonium ion will act as the acid because it wants to get rid of that hydrogen, and it will give it to the hydrogen carbonate ion to form hydrogen carbonate plus ammonia. So you can see here the hydrogen carbonate ion is amphiprotic, meaning that it can act as either an acid or a base depending on what it's put with. If it's put with water, it will act as an acid. If it's put with ammonium, it will act as a base. Here's just a little example here. You can see that water acts as a base when reacting with hydrochloric acid and as an acid when reacting with ammonia. So, water is also described as being amphiprotic. It can act as a base, which is done in the first example here. It's accepted that hydrogen, or it can act as an acid and give up that hydrogen to create hydroxide ions. So amphiprotic substances are in the middle here, and you can see they can act either way. Okay, so in your booklet you've got a couple of questions that you can now have a go at, and there's some chapter questions there to get on with as well.